Hello guys, in this video we're going to cover linear predictors, both classification and regression. So let's understand one of the most fundamental concepts behind machine learning. Almost every model from logistic regression to neural networks starts with this simple idea: multiply features with weights and produce a score. So what is a linear predictor? A linear predictor is a function that predicts an output using a linear combination of input features. So mathematically, it is a dot product of score. The input samples and feature vectors. So well, x is input sample in this equation. X is input sample. Phi of x is feature vector. W indicates weight vector, and this indicates score prediction value. Think of it like prediction equals weighted sum of feature. So the feature vector is basically a transformed representation of the input. This means we convert a sample input x into d number of features. So here each one indicates one feature. You can think of the feature vector as the measurable properties of data. For example, in house price prediction, let's say input is house, and the feature vector will become area, bedrooms, age, something like that. In image classification, input is image. Features could be edge count, texture value, or let's say pixel intensity. So machine learning, basically AI, it never works directly on raw input. It works on features. So we multiply the feature with weights. So basically, this each weight tells how important a feature is. For example, let's say large weight indicates high influence, small weight low influence, and negative weight its inverse effect. Now we compute the score. This is an inner product, let's say, or dot product, and we multiply here. It means we multiply each feature with its corresponding weight and add them together to get a score. So if we view it in uh, in a geometrical way, feature vector is let's say feature vector is a point in a d-dimensional space. Weight vector is direction. Score is a projection of feature vector onto the weight vector. If projection is large, then it's a strong prediction. Okay, now let's see if in the decision making in the classification case. So we often use the scores like +1 and -1. So this is basically a binder classification. This forms a linear decision boundary, a line or a hyperplane or a plane. Sometimes data is not linearly separable, so we transform features. So now linear model in feature space becomes nonlinear in input space. This is the foundation of polynomial regression kernel methods, SVM. So linear regression, linear regression, logistic regression, perceptron, SVM with linear kernel, and final layer in neural networks. These five are real world models using linear predictors. So to summarize, input is converted into a feature vector. Each feature gets a weight. A weighted sum is computed, and that sum becomes a prediction score. Simply this equation is the backbone of modern machine learning. We can say like that. So now let's move from linear predictors to one of the most important applications: classification. What is a linear classifier? It separates data into classes using a linear decision boundary. We are given a weight vector and a feature vector, and the classify function computes the dot product between the weights and features, and then we take the sign of the result. If it's a positive, then it's class 1, negative class 2, or it will, if it's a 0, then it's exactly on the boundary, on the decision boundary. So the decision boundary here is defined by the dot product of weight vector and feature vector equating to 0. So this forms either a line in 2D or a plane in 3D or a hyperplane in higher dimensions. You can see two clusters, blue and red here. The straight line between them is the decision boundary. Points above one line, one class. Below line, from other class. They belong to other class. Now, margin. So the margin is basically it tells not just whether the prediction is correct or not, but how confident it is. If the margin value is positive, large positive, correct, then it means correct and confident. If it's a small positive, correct but it's not sure. If it's zero, it's the point is on boundary. If it's negative, then it's a wrong prediction. For example, if the score is plus 3 and the true label is plus 1, then margin is plus 3. It means it's a good prediction. If the true label is minus 1, then the margin equals minus 3 is the wrong prediction. So the insight here is larger margins mean better classifiers. That's why models like SVM try to maximize the margin. Now let's move to regression, where instead of classes we predict continuous values. So we are given a weight vector and a feature vector, and obviously the prediction is that it's dot product. But in regression we don't take the sign. The score itself becomes the prediction. If, for example, uh, if the features are area, bedrooms, age, the prediction could be let's say a house price or a rent value. So the residual is mm, basically the measurement of error. We simply is simply the difference between the predicted output and the true output. If the residual is 0, it means a perfect prediction. If it's positive, it means overestimation. If it's negative, it's underestimation. So actually, the residual matters because residuals are used to compute loss, train models, and evaluate performance. Common losses built from residuals are uh, squared loss and absolute loss. Uh, with squared loss means let's say mean squared error and absolute mean absolute error. So in summary, linear classifiers use the sign of weighted sums. Decision boundaries separate classes. Margin measures confidence. And linear regression predicts continuous values. Residuals measure prediction error. These concepts have formed the mathematical backbone of supervised machine learning. Thank you.